Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today it is the 14th lecture of this course and the topic is interference of waves. First, I will give the learning objectives. Applying the principle of superposition, the student will understand to show that two overlapping waves add algebraically to give a resultant wave. Also, for two transverse waves with the same amplitude and wavelength that travels together, they will be able to find out the displacement equation for the resultant wave, and also they will be able to calculate the amplitude in terms of the individual wave and the phase difference. Also, they will be able to describe how the phase difference between two transverse waves can result in fully constructive and destructive interference, and also they will be able to understand the concept of intermediate interference. With the phase difference between two interfering waves expressed in terms of wavelength, they can also express that in terms of the phase difference and also in terms of the wavelength. They will be able to quickly determine the type of interference the waves have. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. In this lecture, we have taken some of the illustrations from this book. Okay, we start with the principle of superposition. It often happens that two or more waves passes simultaneously through the same region. For example, when we listen to a concert, for example, sound waves from many instruments fall simultaneously on our eardrums. Now, that can be discussed here generally based on the principle of superposition. So, when two waves overlap, we see the resultant waves, not the individual wave. For example, at this portion, this wave and this wave is approaching at this point. Now, this is that point at which the wave combine. So, at this point, we will see the resultant waves, and for example, this dashed line represents the amplitude of this approaching wave, and this dashed line represent the amplitude of this approaching wave at this point, and at this point they combines to give us a resultant wave. Now, suppose that two waves travel simultaneously along the same stretch string, as we have discussed the wave on a stretch string. Now we have two waves that is approaching a point, that is, they will pass through that point. Those waves will pass through that point. So at that point, the wave one can have the resultant waves. Let we have y1 and y2 be the displacement that the string would experience if each wave travel along. The displacement of the string when the wave overlap is then the algebraic sum, as I have explained graphically here. So if you remember, this is the representation of one wave and this is the representation of another wave. Let's say this is y1 and this is y2, and this y prime will be the resultant wave. Now this prime doesn't mean any derivative. This is just a symbol used by your book for the resultant wave of the y1 and y2. Now this overlapping wave or the resultant wave, the overlapping wave algebraically aid to produce a resultant waves. And also the overlapping wave do not in any way alter the travel of each other. Now based on these description, we will be discussing the interference of waves, that is the individual waves will add up algebraically. So suppose we send two sinusoidal waves of the same wavelength and amplitude in the same direction along the stretched string. Remember, in the next lecture we will be describing these interference, or we can say the addition of these waves uh, having different amplitudes, but in this topic we are considering waves of the same wavelength and amplitude. So if we send two sinusoidal waves of the same amplitude having all these parameters same, what we are expecting? So the resultant wave depends on the extent to which the wave are in phase with respect to each other. That is, the rest of the parameter are the same, either they are different in terms of their state of motion, as we have discussed the state of motion in terms of phase. That is, how much one waveform is shifted from the other waveform. So that resultant wave depends upon the following two conditions. That is, if the waves are exactly in phase, right, having the rest of the parameters are the same, we will see the mathematical descriptions of this slide in a minute. But first we are discussing these conditions. That is, if the approaching two sinusoidal waves are having the same wavelength and amplitude, and also they are exactly in phase, so they combine to double the displacement of either wave. Also, if the approaching two sinusoidal waves are exactly out of phase, they combine to cancel everything and the string remains straight. So depending upon these two conditions, the resultant wave can have either having maximum displacement or minimum displacement. So the phenomena of combining waves is known as the interference of waves, and the waves are said to be interfere. So now we will see the representation of two waves through that y1 sine of kx minus omega t, and also y2m sine of kx minus omega t. So now, to understand this mathematically, let one wave traveling along the string is given by this thing. That is, the first wave is having y1 equal to amplitude ym in and that is sinusoidal, having kx minus omega t. The second wave is slightly shifted by this angle phi. So you see, the amplitude of the first wave and the second wave is the same, having the same lambdas because having the same k, and also having the same angular frequency omega. They are only different by this angle phi, which represent this phase difference. Now the phase constant that depends upon the two waves. That is, how much the two waves are out of phase. Now, using the superposition principle that we have discussed on the previous slide, we can add these two waves such that this is the resultant waves and using the expression of y1 and y2 here, so that we have ym sine of kx minus omega t and also ym sine of kx minus omega t plus phi. Now, using this sine alpha plus beta formula, which is given in your textbook in the appendix E, you can simplify these things using this sine alpha plus sine beta equals to this thing. One can simplify the expression for the resultant waves as this one. Now, this represents the amplitude of the resultant wave. This thing is the amplitude. If this one is the displacement and this is the amplitude. Now, if we see this ym is the amplitude and ym is the amplitude of the second, but the resultant wave amplitude depends on the angle phi. That is, and also the third is the oscillating term, that is the resultant wave is still sinusoidal in nature. Now we will see the outcomes as we have discussed on the previous slide, that it depends upon the state of motion, the relative state of motion between the two waves, so that if the phi equal to 0, that is they are exactly in phase, so that if we put phi is equal to 0 in this expression, which is the expression for the resultant wave based on the superposition principle, so that we'll be able to get 2ym, so that this factor goes to 1 and this is 0, so that we have sine of kx minus omega t, and this goes to 1, you have left with 2ym. So that if we remember on the previous slide, I told you if the two waves are exactly in phase, having all the parameters, the amplitude and the lambdas are equal, the resultant wave's amplitude will be double. Now, if this phi or the two waves are out of phase by pi radian, so that we'll be getting a 0 amplitude of the resultant waves, as we have discussed that the string will be straight. So this is the case of the constructive interference, and this one is the destructive interference. One can have an intermediate interference depending upon the angle phi. If this phi is in between 0 and pi, so that will be the intermediate interference. When the interference is neither fully constructive or nor fully destructive, then it is said to be intermediate interference. Now, the amplitude of the resultant wave is then intermediate between 0 and 2m, that is, it will be in between maximum and minimum. The maximum is 2im, that is, it will be double, and the minimum is 0. So, in case of the intermediate, we'll be having in between the 0 and 2im. Now, we can describe these mathematics graphically. So we have one wave represented by y1 and the second wave represented by y2, such that the wave is out of phase by an angle phi. The resultant wave is having this expression based on the superposition principle. Now we can discuss the three cases, the constructive, destructive and intermediate interference graphically. So this one is the first wave, y1 is, let's say, represented by the blue line, and y2 exactly having the same parameter ym, lambdas, and also the phi is 0, so that's why they are identical. So once the phi is 0 and these two waves are traveling along the positive x direction, as one can find out with the help of the, 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 the argument of the sine function. So in that situation, the amplitude will be doubled. That is, y prime will be equal to 2ym, and still it is sinusoidal. Now, if we have y1 represented by this blue line, and the other one, the y2, which is out of phase by phi, so that they are exactly out of phase, and then the resultant wave will be just a straight line having zero amplitude. So that is the descriptions of destructive interference graphically. In case we have a phi in between 0 and pi, that is, in this situation, this is the one wave and the second wave have a phase difference of 2 or 3 pi. So in that situation, the amplitude will be in between the maximum and minimum, which can be obtained by this mathematical expression as well. Now, this description of constructive and destructive interference can also be done in terms of wavelength. For example, on this slide, we are discussing in terms of the phase difference phi. One can also do it in terms of lambda. For example, phase difference can be described in terms of wavelength as well. For example, in this second situation, in the middle one, the wave may be said to have 0.5 lambdas out of phase. That is, the one wave is behind by 0.5 lambda from the other wave. So in terms of lambdas, we can describe the constructive and destructive interference. If the waves are, let's say, one wave is behind the other wave, for example, in this case, they are 0 lambda difference between the two waves. If there is a difference of 1 lambda, still there will be constructive interference. But if the difference between the two waves is half lambda, so then it will be destructive interference. Now, these descriptions are taken from your course book. Now, one can summarize the resultant wave, which is based on the superposition principle, in terms of the phase differences that can be either expressed in degrees, in radians, in lambdas, the wavelengths. For example, we see if there is a 0, phi is equal to 0, that is the difference between the two waves is 0, or we can say that they are 0 lambda apart. So in that situation, we'll be having constructive interference, and the amplitude of the resultant waves will be double. Now, in this situation, when the two waves are, let's say, there is a phase difference of phi, or they are 0.5 lambda apart, so in that situation, we'll be having a destructive interference. See, the sinusoidal function repeats its value after 2 pi. So again, if there is a phase difference, is 2 pi, or they are 1 lambda apart, still we will be having a constructive interference. The other situations are for the intermediate interference, as we have discussed. Now you need to go through these 4 questions, which is based on the interference of waves. For example, in the first question, you need to find out the resultant amplitude if the two waves are having a phase difference of pi by 2. So using that resultant wave expression, you can find out the amplitude of the resultant waves. And with this, I need to thank you for your